Hey everyone, and welcome back to Tech Fails, the channel where we dive deep into the biggest botches, breakdowns, and blunders in the history of technology. We talk a lot about simple failed products and sunset projects like the Zune or Google Glass. But today, we're looking at something far more monumental, a failure that threatened decades of scientific progress. This is the story of a massive historical technical disaster. We're talking about what was, arguably, one of the greatest near misses, one of the most embarrassing technology scandals of the 20th century. This was a mistake so catastrophic that it cost US taxpayers billions of dollars and nearly ruined NASA's reputation. We're going back to the launch of the Hubble Space Telescope. The focus today is on the microscopic yet monumental engineering oversight that turned the world's most anticipated observatory into an almost entirely useless paperweight. The total cost of this program had already ballooned to over $1.5 billion by the time it was ready for launch. The world was truly expecting perfection. To understand the scope of this failure, you have to understand the sheer hype surrounding Hubble. This was not just another piece of hardware. It was humanity's literal window to the universe, designed to change everything we knew about space. For centuries, our view of the cosmos has been hampered by one major thing. That main obstacle is Earth's atmosphere. The air we breathe, the clouds, the light pollution, it all blurs and distorts the light from distant stars and galaxies. It's exactly like trying to read a street sign from a mile away while you are completely underwater. Scientists knew the answer was simple. Get a telescope above the atmosphere. Once above the atmosphere, the images would be revolutionary. They would be perfect. The idea for a space telescope had been discussed since the 1,920 seconds, but it didn't really gain political or financial traction until the 1,970 seconds. This project was a massive joint venture between NASA and the European Space Agency, known as ESA. It was fittingly named after Edwin Hubble, the man who confirmed the existence of galaxies beyond the Milky Way and the expansion of the universe itself. The numbers of the project were just staggering. The telescope was designed to be the size of a large school bus, requiring 2 massive solar arrays to power its complex systems. However, the absolute heart of Hubble, the critical piece that mattered most, was the primary mirror. This component had to be beyond perfect. The required smoothness and curvature of the mirror were incredibly precise, demanded to be accurate to within 1/2,000th the width of a single human hair. This precision is truly an insane degree of engineering capability, pushing the absolute limits of 20th century technology. The project was riddled with typical issues for such a monumental task. It faced years of budgetary battles and scheduling delays, a very common feature of historical technical disasters. Initially slated for launch in 1983, the program was severely pushed back by years due to the devastating Challenger disaster in 1986. Finally, on the 24th of April 1990, the moment arrived. The Space Shuttle Discovery carried the Hubble Space Telescope into orbit. The deployment sequence went flawlessly and without a hitch. Everyone at Mission Control breathed a collective sigh of relief, thinking the hardest part was over. The ultimate test of the mission, however, would only come when the telescope was activated and started sending back its first images. NASA held its breath, and then those first pictures started to trickle back down to Earth. The excitement quickly turned into confusion, then horror. Instead of the crystal clear, stunning images everyone had anticipated, the pictures that arrived were undeniably blurry. They were not completely unusable, perhaps, but they were certainly not what a 1.5 billion cutting-edge observatory should be delivering. Something was fundamentally and catastrophically wrong. Imagine buying the most expensive, highest definition 8K television on the market today. Then you plug it in, and you find that everything on the screen looks like it's being viewed through a greasy, hazy window. That was the immediate sinking feeling of the initial reaction to the images. The scientific term for the flaw was spherical aberration. This is, simply put, a focusing error. The images were hazy, out of focus, and utterly unacceptable for groundbreaking science. This wasn't a minor tweakable flaw. It was a fundamental, mission-killing design failure in the very component the entire mission was built around. The entire premise of the telescope relied on the primary mirror being perfect. When light hits a perfectly parabolic mirror, all the light rays converge at a single, perfect focal point. That is the physics of it. However, If the mirror's curvature is even slightly off, the light rays that hit the edges of the mirror focus at a different point than the rays that hit the exact center. This difference in focus points is spherical aberration. That difference caused the haze. The scientific community was absolutely horrified, and the international press had a field day, calling it NASA's billion-dollar blunder. NASA was immediately forced to confront a brutal truth. They had spent years and billions of dollars launching a defective piece of equipment. The immediate priority shifted entirely from exploring the universe to conducting a massive, rapid-fire engineering autopsy. They had to figure out why the mirror was flawed and find the culprit of this terrible technology scandal. The investigation eventually led to one company. That company was Perkin-Elmer, now part of Raytheon, the contractor responsible for designing, manufacturing, and polishing the massive 8-foot mirror. What the official investigation uncovered was not a malicious act or a deliberate cutting of corners, which might have been easier to explain. The true cause was far worse. It was a classic case of profound engineering oversight, compounded by a complete breakdown in quality control and rigorous testing. This, my friends, is the classic recipe for a devastating historical technical disaster. The error, as it turned out, was microscopic, located in the primary measuring device used to verify the mirror's curvature. This device was an incredibly specialized instrument called a reflective null corrector. This tool was the only thing standing between the telescope and the atmosphere. The null corrector is essentially a specialized tool with 3 main lenses designed to precisely check if the mirror is polished to the correct, perfect parabolic shape. Perkin-Elmer's technician had meticulously assembled this null corrector. But here is the catastrophic key, the microscopic detail that almost doomed the project to oblivion. One of the corrector's field lenses was manufactured with a slightly incorrect radius of curvature. This was a small, initial manufacturing tolerance error, an annoying but common mistake. But that small error was severely compounded by the fact that the lens was then installed with a tiny gap. This gap was only about 1.3 millimeters between the lens and its mounting plate. This tiny gap had massive consequences for accuracy. In short, the one precision instrument designed specifically to ensure the mirror was perfect was itself defective. It was compromised from the start. When the technicians used this flawed null corrector to measure the mirror, it dutifully told them the mirror was perfectly shaped. But in reality, what the device was actually telling them was, your mirror is perfectly shaped to compensate for the flaws in my own measuring device. They had achieved precision, but precision based on faulty inputs. They had, in effect, polished the mirror to the wrong shape, a mirror that would only produce perfect images if viewed through the flawed null corrector itself. The flaw was not in the polishing, but in the guidance system. The revelation of the flawed null corrector was shocking, but the investigation didn't stop there. It went deeper into the company's internal procedures. The deeper dive into Perkin-Elmer's process revealed a disturbing reality. This disturbing reality, sadly, is all too common in large, complex government contracts. A failure of redundant testing. Any good engineering project, especially one worth billions, must employ redundancy and fail-safes. If you have one primary test, you must have a secondary, entirely different test method to back it up and cross-check the results. Perkin-Elmer did have a second, independently built testing device. This was a backup null corrector, and they had indeed used it. Here's the absolute kicker. The measurements taken by the backup corrector did not agree with the measurements from the primary one. The backup was showing a slightly different curvature. This was the flashing red light, the fire alarm that should have stopped the entire operation immediately. It was the scientific proof that something was wrong, yet it was ignored. But instead of halting production and launching a full investigation into the massive discrepancy, the internal team at Perkin-Elmer made a fatal decision. They were under intense pressure to meet impossible deadlines and keep the budget down. They ultimately dismissed the data from the backup corrector. They convinced themselves that the primary one, the one with the fatal 1.3 millimeters error, must be the correct one, and the backup must simply be flawed. They simply chose to believe the data from the tool that told them what they wanted to hear. This wasn't just a technical mistake. It was a systemic failure of quality assurance and engineering integrity that resulted in a billion-dollar loss. In the high-stakes world of space technology, you cannot afford to ignore conflicting data. When one test says A and the other says B, You stop everything and find out exactly why they are contradicting each other. They failed spectacularly to do that. The mirror was declared perfect, sealed up tightly in the telescope's housing, and launched into space. The initial failure was an absolute disaster for NASA's hard-earned reputation. The Hubble was supposed to be the jewel of space exploration. Instead, it had become a global punchline, a textbook example of a major technology scandal. The immediate and terrifying question then became, can this be fixed? If so, how do we possibly fix a telescope floating hundreds of miles above the Earth? Unlike most satellites, which are one-and-done pieces of equipment, Hubble was intentionally designed to be serviced while in orbit. This foresight, which was originally just for routine maintenance and upgrading instruments, suddenly became the mission's only lifeline. This ability to be serviced was the only thing standing between the Hubble project and total, permanent failure. The repair mission, officially designated as Servicing Mission 1, or SM-1, was one of the most complex and high-stakes missions NASA had ever conceived of. It was essentially the astronomical equivalent of a massive, high-precision eye surgery performed in the unforgiving, vacuum-sealed environment of space. The core of the solution they engineered was brilliant in its simple practicality: corrective optics. Since there was absolutely no way to physically take the primary mirror out and repolish it, they decided to launch a set of secondary, much smaller mirrors. These small mirrors were designed to precisely counteract the flawed curve of the primary mirror. This corrective instrument was named COSTAR, which stands for Corrective Optics Space Telescope Axial Replacement. You can think of this COSTAR package exactly like a pair of customized prescription glasses for the giant telescope. The COSTAR package contained tiny, specially figured mirrors designed to physically unblur the image. They would refocus the light perfectly before the image reached the telescope's main scientific instruments. It was an incredibly elegant, yet difficult solution. To install COSTAR, the astronauts had to replace one of Hubble's original science instruments, the high-speed photometer, with the corrective lenses. It was a tough trade-off for the scientific community, sacrificing one specific capability for the entire telescope's functionality. The repair mission was launched in December 1993, a staggering 3.5 years after the flawed initial launch. It required the Space Shuttle Endeavour and a crew of 7 astronauts. They spent 11 days in space, performing 5 incredibly grueling spacewalks in an environment that was utterly unforgiving and perilous. This wasn't just a technical mission for NASA. This was a massive public relations lifeline. The world was watching closely. The spacewalks were televised globally, showing astronauts wrestling with massive, custom-built equipment in zero gravity. They had to carefully remove the old components and then precisely install COSTAR and the new Wide Field and Planetary Camera 2, or WFPC-2. This camera also conveniently had corrective optics built right into its mechanism. The tension across the globe was palpable. If the astronauts dropped a critical tool, if a seal failed, or if the corrective optics themselves were even slightly off from their calculations, the mission would fail, and Hubble would be rendered permanently useless. But the crew of Endeavour executed the mission flawlessly, with unbelievable precision and bravery. They truly were heroes in that moment. After the servicing mission, once all the new instruments were thoroughly tested and powered on, the world held its breath once more. The corrected Hubble took its first test image, a picture of a distant nebula. The results were instantaneous, stunning, and completely breathtaking. The images that came back were, for the very first time, exactly what they were supposed to be. They were perfect. Gone was the debilitating haze and blur. In its place were crisp, clear, stunning visuals of the cosmos. This was the cosmic redemption NASA, the ESA, and the entire scientific community had waited years for. The telescope that was once an embarrassing historical technical disaster had officially become one of the greatest technological achievements of our time. It has now operated for well over 30 years, defying expectations. It has given us a literal front-row seat to cosmic history. Its iconic images, the famous Pillars of Creation, the awe-inspiring Hubble Deep Field, and countless others have fundamentally redefined our human understanding of the universe. The Hubble mirror flaw is a case study that goes far beyond a faulty piece of glass. It serves as a powerful cautionary tale about the pitfalls of high-stakes, complex technology projects. It is a recurring, consistent theme in the history of tech fails. The single biggest failure was trusting a single measurement system without adequate, independent verification. Any mission-critical component must have cross-checked, redundant testing protocols. Ignoring conflicting data is a complete failure of engineering integrity, which almost cost the entire project. The second lesson is to beware of schedule and budget pressure. The team at Perkin-Elmer was under immense pressure to deliver, which contributed to the disastrous decision to dismiss the conflicting data. When deadlines clash with quality control often loses. Finally, the power of repairability is the final lesson. The one thing that saved the project was the foresight to design it for servicing and maintenance. Designing for failure and repair is just as important as designing for initial success in complex projects. Ultimately, the Hubble story is a tale of incredible human ingenuity and resilience in the face of failure. After the initial embarrassing technical disaster, the scientific and engineering teams didn't quit or panic. They found the root cause, engineered a highly sophisticated, high-stakes solution, and executed it perfectly. The Hubble telescope, in its early life, was a cautionary tale of a profound engineering oversight. It was a billion-dollar mistake that almost ended in disaster, but the subsequent servicing mission became a beautiful testament to human determination and problem-solving. It proved that sometimes the greatest technological achievements aren't the products that launch perfectly on the first try. They are the ones that we fix, upgrade, and ultimately redeem through ingenuity. The Hubble Space Telescope now floats above us, a flawless eye on the cosmos, delivering images that inspire and educate millions. And every time we see one of those stunning, crystal clear shots, we're looking at the result of a profound mistake that was brilliantly corrected. That's all for this week's dive into tech fails. What's the biggest engineering comeback story you know? Let me know about it in the comments below. Don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next deep dive into history's biggest technological blunders. We'll see you next time.